In this tutorial, we'll be going over integrated rate laws and how to analyze test plots for first order, second order, and zero order integrated rate laws if you're given a set of data. So this first slide is kind of like a review of first order integrated rate law. And so if you set this one, and remember the problem with this was you get like these inconsistent rates. Because if you measure them at different times during a reaction, you're going to get a different rate because it tends to decrease over time. And then the problem with this was the method of initial rates. This is only measured initially when time is close to zero, is when that rate is measured. So there's no like time dependence. So when you set them equal to each other and you integrate the function, then you get this. So, and then we have this useful fraction form. This is exactly the same thing. It's just applying this log property, and you get like this useful fraction form. But this and this are the same exact equation. They're just a little bit converted, a little. This one here. Um, okay, so this one here is when you move this term over, and you can come up with this new form. Okay, so moving on, we have a second order rate integrated rate law. So this is a you get a similar um, it's a similar concept as applied where we can't really use the one where you measure the rate over time, and you can't really use the method of initial rates either because that doesn't show time. So you get a different function where instead of natural log, you get the inverse of the concentration is equal to, and that's what you're seeing here. So the inverse of the concentration is equal to 1 over the initial concentration plus K times T. And this is the second order integrated rate law. And remember, these all depend on whether it's first or second order. What it actually means, and we're going to see more on this later, what it actually is telling you is how many molecules are involved during the collision, and this affects the math relationship between the rate and the time. Um, One thing that I should point out, though, when you're using these, what's so special about these equations is the fact that it has time, and these two equations, they allow us. What they do is they allow us. They're very powerful because they allow us to answer a question like this: is like how much reactant remains, which is this. Notice that this is not initial. So we can answer a question like how much reactant remains at some later time during the reaction, which oftentimes you're interested in this question because let's say you take like some type of medicine and you want to know how long that's going to be in your system. So how much of that initial molecule will be in your body, um, like 3 hours after you take it. Okay, so if you know the relationship here, then you can answer that question. If you know what the rate constant is and how much you initially took, how much of the medication you initially took. So that's what's so great about these integrated rate laws is the fact that it shows the dependence on time, and it relates it to some amount at a later time. So this amount right here is at a later time. Okay, because we're using like these big fancy words like integrated rate law and like okay, so we need to take a step back and see what this is actually useful for. Okay, like why even look at this? So that's the power of this equation is it you can figure out like how much remains at some later time. And some happen to involve more molecules during their reaction process. That would be a second order. And if it involves less molecules, then that would be first order. And if it involves no molecules, that would be zero order. If it doesn't depend on concentration at all, then that would be zero order. Okay, and I kind of have like this nice summary slide later that we'll look at. that shows a summary. So here's the relationship. So if you have second order, can you set that equal to its rate? So the change in concentration over time, and integrate it, then you'll get this function here. You'll get this line function. Notice the slope is positive on this one. So you'll see if you do a what's called a test plot, you'll see that this results in a plot with a positive slope. So you'll see that k is positive, whereas before on this you see that slope is negative here. So if you do a test plot here, you're going to get a negative slope. And what do I mean by test plot? I'll show you on an example problem. We'll take a look at a couple example problems. Um, okay, so I actually have this. You'll see this available as an attachment on the school's website. So I have this chart here, so and it kind of like shows a summary of the rate law, um, what the test plot looks like. So if it's zero order, basically the rate does not depend on if it's zero order. The rate of the reaction does not depend on concentration of the reactant. So you're gonna see um, that over time, the constant if you plot concentration versus time, you'll see that the concentration steadily decreases over time, and you'll see a linear relationship. And what that means is the amount that you have from here to here will not depend on how much is left over at this point. That's what that's going to end up meaning. A test plot for natural log versus temperature. Um, if this gives you negative slope, so if you have natural log of concentration versus time, and if this ends up with a negative slope, then this is going to be first order. And if you do inverse, so if you do 1 over the concentration and you look at the graph of this over time, you'll actually get a positive slope. Um, this is because over time this amount is actually decreasing, but you're taking the inverse, so you're plugging in smaller and smaller numbers here over time. You'll be plugging in smaller concentrations, but since you're actually taking 1 over the concentration, you actually end up getting bigger and bigger answers over time. So that's why you end up with a positive slope there. Um, the equation was actually on the slide before. It's 1 over equals 1 over the initial plus k times t. So that's the second order rate law. The special form for the zero order doesn't really have a special form. The first order has like this special fraction form that's really useful. I found it useful in some problem solving. This right here is the fraction left over at some later time, which is actually t. This later time I'm mentioning is actually t here. So it's kind of useful sometimes. So that's why I have this special row here. And half-life is something we'll get into on probably another tutorial, but we'll be looking at these graphs more closely and analyzing what they mean, what each one of these graphs means, and what half-life means. All right, so let's try a problem on this. What I mean by when I say test plot here. So if you're given some data and they give you nothing else about the problem, but they give you some measured data of certain concentrations measured over time, if you do a test plot, so convert the data into natural log of concentration and graph it versus time, And if it results in this negative slope, then you can tell by looking at the graph that that reaction is a first order reaction. If you get some weird looking graph that's like some curve or something, then it won't be first order. Then you should try a second order plot and try graphing the inverse of all the concentrations versus time. And if you end up with a positive linear relationship, then you'll know that it's second order. And if you get some weird answer here and you get some weird graph here, then it's probably zero order. So try just graphing it. Usually you could tell if it's zero order or not just by inspecting the data. And I'll show you what I mean. It's better if we look at examples to describe what I'm mentioning here. Okay, so I have this also available as an attachment, so you'll see that it's a green titled slide, but it's not required to write this. I have this whole thing on. It's just kind of like a reference handout. So I have this all printed out, typed up on a separate handout, and I'll put that also on the school's website. So, and I'll walk you through these steps when we go and do a problem. So you go into stat. It's similar to when we did the vapor pressure equation. I think it's called the Clausius-Clapeyron equation, or Clapeyron equation. So you'll it's similar. You enter the plotted points, and then you graph it. It's going to be super zoomed out, so you're going to want to zoom in, and I'll show you how to do that on your TI calculator. And again, all these steps are typed up and printed out. You could find it. Don't waste time writing all this stuff. Okay, so okay, yeah, and then to get slope. So, and the good thing about these, I kind of didn't mention this point, kind of an important point here, but another kind of key thing about when you graph this is your calculator can, since it's in line form, it can calculate slope for you if you have all those data points. And the good thing about that is what slope is actually the rate constant is actually what slope is. And that's also really powerful. Okay, once you have all those data points, you'll not only know what order it is, you'll also know what slope is, so that means you'll also know what k is in both cases. So let's not waste any more time and go right to a practice problem. So, um, okay, so we could try this. We could actually try this in class. Um, Actually, I kind of want to see what you guys do in class. So the AP exam, I know in the old style, they always used to ask what the units for K is, like specify what the units are for K. And it's pretty easy to figure out is if you just understand what a rate is. So a rate is concentration of a reactant over time. So it's going to be a rate. The concentration is going to be molarity over time. And I'm just going to put seconds here, but it realized it could be minutes, hours, or days, depending on the reaction. Like if it's super slow, you would do it in days. If the reaction's fast, you would do it in seconds or milliseconds or something like that. So for the units for K, this says the directions here are plug in only I should say the units into zero first order and second order rate laws, and then solve for the units for K. So our units for K are going to be exactly what um, the units are for the rate. So rate is molarity per second. So that's going to be, for zero order, those are going to be our units. I'll do the first two, and I want to see what you guys do for the second order. Okay, so for first order, rate is typically molarity over seconds. And I'm going to write it out like this. Molarity over seconds equals K times, and this is, realize, so this is to the first power, so K times molarity. Now the directions say solve for K. So to solve for K, I'm going to divide both sides by M. So dividing both sides by m, I can get my units for k. So k for first order are going to be, the molarity cancels out. The units for k for a first order reaction are going to be inverse seconds. And so for second order, I want to see what you guys do. So for rate, you're going to plug in molarity per second, and then you're going to have time k times, and this is concentration, so it's going to be molarity squared. Okay, so rearrange this and then solve for k. So I'll check to see what you guys come up with on that problem. Okay, so onto the test plot, because it's important to go over this exercise, because when you enter your test plots into your calculator, it's not going to really show you what units the k is. So this is good to look back at, and so you can check and see what the units are going to be for k. All right, so let's do a test plot problem. So this problem says, it doesn't really tell us what order it is. It says um, how much reactant is left over after 3 hours, and our graph here, it doesn't go to 3 hours. It goes to 130 minutes. 130 minutes, which is 2 hours and 10 minutes. So 3 hours is completely off this chart. But if we know what order it is, we'll know what integrated rate law to use. We'll know to use, is it zero order? So is it zero order? If it's zero order, then we're going to use the zero order rate law, which is just this, minus negative kT. If it's first order, so if it's zero order, this is the equation we want to use. And we would plug in 0.086 here, and we will plug in 3 hours here, or actually 180 minutes. You'll see that when we solve for k, it's going to be in minutes because our data here is in minutes. And then we would solve for that variable, but we don't know to use that equation because we need to do a test plot first. If it's first order, then we would use this equation. And if it's second order, we're going to use this equation, 1 over the initial concentration plus kT. Okay, so what is it, zero, first, or second order? So this is what we do. We need to, first of all, make sure that the temperature, not temperature, the time is on the x-axis. And on our TI calculators, this is going to be our L1 list. So our concentration needs to be on the y-axis. This is our y data. And so this, in our calculator, this is going to default in our stat plot to the L2 list. So if you get these flip-flop, you're going to get a weird answer. So let's go into our calculator here. And let's clear out some whatever we had previously. So I'm going to go into edit, and where I have these L1 and L2. So for L1, I want to enter the times for L1. So I don't have to convert that. I'm just gonna enter it here. So 0, 50, 72, 93, and then 130. So I'll enter that there. Okay, and for L2 is I want to do, I'm simply just guessing here. I'm just going to try first order. I'm actually totally guessing here. This is actually irregular, our times here. So it's a little hard to inspect this and see if it's zero order. Sometimes if we went like 50, 100, 150, 200, and if you notice that this was also correlated directly with those changes, then you could actually tell if it's zero order. But these are actually going up in irregular amounts, which is kind of unusual. But you can't really tell if this is zero order just by inspection. So I'm just going to guess. I'm just guessing right now that it's zero order. I'm doing a test plot. So I want to convert all of these into natural log in my calculator. Okay, so for L2 right here, I'm going to go natural log of all these points here, of all these data points. So natural log 0.0860, enter. Natural log 0.0465, enter. Natural log 0.0355, enter. Natural log 0.0274, enter, and then one more. So natural log 0.0174. You really have to make sure you're pressing all the right numbers. If you miss one number anywhere on here, you're going to get a weird graph. Okay, so enter. Now I need to make sure my plot is turned on, because if I hit graph, nothing shows up because my stat plot is not turned on. So I need to go quit. Okay, now I'm in some weird thing. Okay, now I need to go second function stat plot and see it's actually turned off right there. So I need to hit enter and turn this guy on. And now make sure, so I entered this into, if you screwed up and entered if you entered this into the first column, then you could switch it right here and fix it. So you don't need to go back and re-enter all that stuff. You could switch it right here. So you just scroll down and you can change it. So you would go second function and then L2 right there to change it. But I knew it defaulted like that, so I entered this into my first column and this into my second column. So I should be good here because I turned it on. So I'm going to hit graph, and you'll see my graph is right here because the data points are super small. So I'm going to hit zoom, and I'm going to go to zoom stat, which kind of like auto fits the data, auto fits my graph according to what my data was. So I'm going to just hit 9 instead of scrolling all the way down. Just hit 9, and it automatically graphed it for me. It didn't connect the points because I didn't tell it to. So I'm going to go back into stat plot, and I had the wrong type here. So I'm going to go into that one. I want to select that one and then go back to my graph, and you'll see that it came out as a nice straight linear relationship with a negative slope. So this I just guessed and I got it right, which is an outstanding result. Now I'm done. I don't have to test the other zero or second orders. So I'm done here. I know that this is first order. So if I go back to my question, is like, what equation do I use? I just figured it out. I'm going to use this one. This is the one I'm going to use to answer this question here. But I need to figure out what K is because I'll have too many unknowns. So I need to figure out what K is first. Okay, and then I could plug in 180 minutes here for T, and for the initial, I'm going to plug in this number for the initial. Okay, so I'm going to go ahead and pull up my calculator and figure out what um, K is going to be. So I go to, so I'm going to go to stat and calc, and so this is actually going to calculate the linear regression, the line equation for me if I just hit 4 or scroll down to 4, but I'll just hit 4. And again, if you kind of messed up on the columns, like if you entered this into the first, or if you entered this into the first and this into the second, you could switch it here. But I entered them into the correct columns because I knew it was going to default like this. Okay, so so I know my stuff is entered correctly, and I'm going to hit calculate. And this A value is actually my K value. That's actually my rate constant. So it's going to be 0.01. It's going to be 0.012. And I'm going to go to 2 sig figs since my times here were 2 sig figs. So it's going to be 0.012. That's my rate, my K value. So K equals .012. Notice it was a negative, but in my equation, that there's a negative there to make it a positive. Rate constants always have to be. It's a physical quantity, so it not really a quantity. It's like this proportionality constant term that makes the rate law work. And remember my units for first order. If you forgot, then go back to that slide where we figured out what all the units were for each rate law. It's inverse time, which is actually in this case, it's minutes. So it's inverse minutes. So I'm going to write min to the -1. And now I could answer this question because I know what k is. I know they tell me the time, and I know the initial concentration. So that initial concentration, this number here is going to be plugged into here, that term, and then 180 minutes goes here, and then I know what k is, that goes here, and then I could simply solve for how much is left over. So that's the magic of this equation, is you can figure out some amount that's way off this chart. I could answer anything I want. I could answer how much is left over after 8 hours or 9.5 hours or whatever you want to know. Okay, so like say there's like a poisonous gas. Say you get trapped inside a room and there's like a poisonous gas outside the room. If you knew the rate constant and you knew what order that reaction, the decomposition of this toxin was, you could figure out how long it would take before it would be safe to exit the room. So just remember that in case you ever get trapped in a room, that outside that room there's poisonous gas, if you ever come across that problem. So here's let's continue this problem. So if you have our rate law was the first order, it's going to be natural log 0.0860. And so where this number came from, it came from the chart, the initial amount, and minus our k value, which was 0.012 inverse minutes, and the time is 180 minutes. They gave us 3 hours. Actually gave us 3.00 hours, so we need to convert that to minutes because our k value was in minutes. So now we can solve this problem. And let's see if I have this done ahead of time. Doesn't look like I have it solved ahead of time. So I could pull up our calculator. And this is going to be the natural log of 0.0860. There's actually a rule for the doing natural logs. Actually, come to think of it, I do have this done, which helps a lot. So there's a sig fig rule for logs, and it's the number of sig figs equal the number of decimal places. So in this result right here, I have 3 sig figs, and now in my calculator, when I took the natural log of that number, my result should have 3 decimal places. So it's going to go to the 4, 5 to this 3 right there. So it's going to be 2.453. So this result right here will be -2.453. So this has 3 decimal places. Minus 2.2, which is what I get from this part right here. So I get negative 2.2. Now if I add these two numbers together, I get natural log of some concentration later equals negative 4.7. So if I exponentiate both sides, then I get, to get rid of the natural log, then I get e to the negative 4.7. If I run this through the calculator, I get 0.0091. Um, I do need to check this. If you exponentiate, I believe it's sig figs to sig figs. So since this has two sig figs, your result should have two sig figs, and that's the final answer. So let's take a look and see what this number means according to our chart here. So we barely have any left over, and realize this is 3 hours later. So let's compare this number to our chart. So let's go back and look at the chart for that question. So after 2 hours and 10 minutes, I have this much left. So after 3 hours, I had 0.0091 molar. Okay, that answer seems to make sense. So it's not like some insanely lower number than this. So it's kind of like in line with the rest of this data, it looks to be. So realize that if you get some really strange number, like if you get some number like 0.05 something, that's doesn't work because that number is actually between these two numbers, which would be how much you have left over after like 25 minutes. Okay, so there you could do like some logical checks on your final answer, and usually if you get something really weird like that doesn't match your data, it's probably, check your stat plot. It's probably because you have them in the wrong columns or something like really. It's kind of a minor issue, but it's sort of a major problem if that happens. So because you'll be wondering like what in the world is going on, and it'll take you like 30 minutes to figure out what you did wrong. But go back and check to see if you put these in the correct columns, or if you like if you missed a number. So I entered it real slow. I took my time when I entered these. It's usually something like that. Okay, so I do have a practice problem, and I have it right here. So I have another, this is a test plot problem. It's just like the problem that we just did. And I'll give you a hint here what this is saying. It's saying the rate is zero order with respect to CO. So that means it didn't depend on CO at all. So it's going to be either zero first or second order with respect to NO2, which you should be able to tell from here. And I could tell you right now that it's not going to be zero order, and I'll tell you why. Because this is regular time data, so it goes up by 5 every time. Now look at the concentration. So it decreased by 0.02. Now, if it were zero order, it would decrease by 0.02 every time. So it would decrease by 0.02. And if it were zero order on this next data point, it should go down to 0.06, but it didn't. So I'll tell you right now, this is not zero order. Okay, just by inspecting the data, you can tell that it's not zero order. So if it didn't depend on concentration, there would be a regular incremental decrease with every incremental increase of time. So that's how you can tell if it's zero order, just by inspection. So you don't have to waste time doing a zero order plot checking one. So check if it's first, and check if it's second order. Okay, and enter. I actually flip flop these two. So with uh, according to the one I just did. So remember, this is your X data and this is your Y data, and this is going to be your L1 column. This is your L2 column. Okay, and for first order check, you're going to convert all those to natural logs, and for a second order check, you're going to do 1 over, like 1 over the concentration of NO2. And for first order check, you're going to do a natural log. Okay, and then answer this secondary question here. Okay, and I'll see what you guys come up with in class. Good luck with this question. That's the end of our tutorial here.